third lecture on the method of electrical images. Today we shall first make a comparative study of the four different cases that may arise when a point charge is placed that may arise due to a system comprising of a point charge and a grounded conducting sphere. Due to azimuthal symmetry, we assume that the z-axis of our spherical polar coordinate is the line joining the center of the sphere and the point of the inducing charge. The inducing charge is of magnitude q and is placed at A, which is at a distance d from the center of the sphere. In these two cases, the inducing charge A is placed outside the sphere. So the system comprises of a grounded conducting sphere in front and a point charge in front of it. In this observation that we have worked out in detail in our earlier class, we assume that the point of observation lies outside the sphere. So the image charge q prime was placed at B on the z-axis at a distance d prime, and yesterday we found that the position of the image charge is given by d prime. Since d is greater than a, d prime is less than a, that is the point image charge lies indeed within the sphere, and the magnitude of the image charge is q prime, which is this, and since d is greater than a, the magnitude of q prime is less than that of the inducing charge. In the potential term, if we consider the potential on the surface of the sphere, since the potential is 0, one need to expand the term like this: 1 upon a square plus d square minus twice a d cos theta to the power half, which arises from the inducing charge, and for induced charge the corresponding factor where d will be replaced by d prime. On the surface of the sphere, a is small, d is greater, so such term will be expanded in power series of a by d. And for the image charge, d prime is smaller than a, so the other term will be expanded in power series of this. Let me write it. For this appears as kq and this appears as kq prime, a square plus d prime square minus twice a d prime cos theta to the power half. So this term should be expanded in power series of a by d, and this term should be expanded in power series of d prime by a. Now come to the situation when we want to find out potential at an internal point. So the image charge should be placed outside the sphere. So we have again placed as per notation, image charge q prime is placed at B, and detailed calculation can be performed when we apply the boundary condition that the potential is 0 on the surface. Then we expand both this term as a power series of a by d, because d is greater than a, and since the image charge also lies outside the sphere, this term is also expanded as in power series of a by d prime, and the comparison of coefficient of p0 and p1 gives us this condition that d prime is equal to d and q prime is equal to q. That is, this inducing charge and the image charge are of equal magnitude but of opposite sign, and they coincide at the same point. That is why the field within the sphere is 0. You know that the conductor is an within the conductor the potential is constant, because there is no field within the conductor, and the potential inside is equal to the potential at the surface. Since the potential conductor is a grounded one, the potential on its surface is 0, so it will have 0 potential inside. Now I come to the second part. Here in these two cases, the point charges, the inducing charges are placed inside the sphere. So these are the position of the inducing charge. In this first example, we want to find out the potential at an internal point. So the image charge is should be placed on the other side of the boundary, that is outside the sphere. So this is the position of the image charge. And if we want to expand these two terms, for this term, say D is less than A, so this term must be expanded in power series of D by A, and for this term D prime is greater than A, so this term must be expanded in power series of A by D prime. And if we equate the coefficients of P0 and P1, we land up to the situation thus. The mathematical expression is exactly same. This mathematical expression and this mathematical expression for the position of the image charge and the magnitude of the image charge are exactly same, but the situation is different. Here, since D is less than A, D prime is greater than A, that is the charge lies outside. In this case, D prime was less than A, but here D prime is greater than A. And the magnitude of the induced image charge, magnitude of the image charge is greater than that of the inducing charge. And in this way we can find out the potential and everything. Now come to the last case of this category, when we want to find out the field at an external point when the inducing charge is within the sphere. So as per method of images, we must place the image charge within the sphere. So image charge of magnitude Q prime is again placed at B, and if we want use the boundary condition on the surface, you see that both D and D prime are less than A. So this term is expanded in power series of D by A, and this term is also expanded in power series of D prime by A prime. And on equating the coefficients of P0 and P1, we land up at the result that this is 0. That is to say, the potential at an external point is 0 for such a charge distribution. Since the inducing charge, image charge or induced charge is of equal magnitude as that of the inducing charge, and the induced charge on the surface of the sphere can be placed by a suitable charge or equal to amount total charge placed at the sphere. So we have two charges of equal magnitude and placed at the same point, so the total potential in the external region is 0. These two results leads to trivial case, that's why they are not in general included in the textbooks. So here we make a comparative study of all the 4 cases that may arise from a system comprising of a point charge and a grounded conducting sphere. Now let me first discuss few problems related to this. And these 2 cases are trivial cases, and these 2 are the case of importance. You know that notice that the expression for D prime and Q prime are same irrespective of the magnitude of A and D. First case that I am going to consider is like this. 2 point charges and a grounded conducting sphere. Grounded conducting sphere. So we consider a sphere which is a grounded one of radius a, and we consider a diameter, it is the center of the sphere, it is a grounded conducting sphere. We have a charge q1 placed at a1 and a charge q2 is placed at a2. So this charge, an image charge, will be induced. The image charge will be q1 prime. It will be q1 prime located at a1 prime, and the image charge of this will be q2 prime, and it will be located at a2 prime. So that q1 prime is equal to aq1 by d1, where let me first introduce OA1 is equal to d1 and OA2 is equal to d2. We call OA1 prime is equal to d1 prime and OA2 prime is equal to d2 prime. And the charges, first the magnitude of the charges. q1 prime is equal to minus aq1 by d1 and q2 prime is equal to minus aq2 by d2. Now come to the distances. d1 prime is equal to a square by d1 and d2 prime is equal to a square by d2. So these are the image charge. If we want to consider a potential at this point, then the potential at this point will be a sum of the potentials arising from these two inducing charge and two image charges. So it will be the combination of 4. If we want to find out the potential at internal point, then the image charges will be placed outside, and we know that this will coincide with this and this will coincide with this. Now come to the another point, a dipole, a point dipole or a dipole of in front of a grounded conducting sphere. We have a conducting sphere of radius this. We have a dipole. Point dipole, or a very tiny dipole. We have written it in a enlarged version. This is minus q, this is plus q, this is the location of A, this is the location of B. So the dipole moment P is located in this direction. This is the center. So the image charge of q minus q will be located on OA, and it will be at somewhere, this is, I call it q1, at the location A prime, and it is located at A prime. And this charge will be, this is a plus charge and this will be minus q2, because this is plus, so it will be at B prime. Now thing is to find out what is the value of this. This is the center of the dipole P, so we call OP is a vector D, and this is the dipole moment vector. This dipole moment and is AB the twice S, the notation that we are following. So AP is S. OA, if we look at R minus vector as the position of the negative charge, so this is OA, and we find that this is the R minus vector, this plus this is equal to D. So R minus vector is equal to D minus S. Similarly, this is R plus vector, this is OB is equal to D plus S. For a dipole, S is small compared to R, so we can get the magnitude of R minus magnitude is equal to D square plus S square minus twice SD cos alpha, where alpha is this angle. And we can neglect S in presence, S square in presence of D square, so this approximates to, if we take D out, similarly this term approximates to D. We can make further assumption that we can expand it in binomial series, and we write that R minus is equal to D, and this is 1 minus SD cos alpha. This is power half, so which adjust with this, and R plus is equal to approximates to cos alpha. These are the approximate expressions for the for R plus and R minus. Now coming to the magnitude of Q1. Q1 magnitude is, it will be plus because it is minus. So this is plus A cube by R minus, and Q2, this is minus A cube R plus. The location of this OA1 or OA1 is, this is D prime A square by R minus, and OB1, oh sorry, we have right primes, O, this is A square R plus. So we see that the magnitude of the induced image charges are not equal, since R plus and R minus are not the same. So the two image charges are not of equal magnitude, so no dipole is created. Only dipole could be, the image dipole could be created when alpha is 90 degree. When alpha is 90 degree, then the situation will be like, then the situation will be look like something, this distance and this distance and this distance will become same, that is OA and OB will be the same. In that case, this will be a, this and this, those two image charges will be of equal magnitude but opposite sign, and again a dipole, if this was the moment of the dipole, it will be the direction of the dipole. This is a very special case when alpha is 90 degree. If alpha is not 90 degree, no dipole is, the image charges do not form a dipole. Now I come to a situation or the justification for the name, the method of images. I want to first give a justification why the method is called method of images by Lord Kelvin. If we have a plane charge, a conducting plate, we have a conducting plate and the point charge is placed Q at A, which is at a distance d, 0, 0, this is the z-axis, and image charge we obtained at Q prime at B minus D, 0, 0, and Q prime was equal to minus Q. If we consider it to be a plane mirror, then the image, if we have an object at a distance d on one side of the mirror, the image will be formed at equal distance on the other side of the mirror. So this connects that d and d prime are equal. And furthermore, this is the real object and this is the virtual image. So the magnification is V by EU is equal to minus 1. Here we connect it by image charge by the inducing charge, which leads to Q prime is equal to minus 1. So the image formation due to the induced charges, that is the charges that are induced on a grounded conducting sphere in presence of a point charge, can be looked upon as simply as the image formation in plane mirror. Let us now consider the other case, a point charge in front of a grounded conducting sphere. We have a point charge Q at A, which is at a distance d, 0, 0, and we found that the image charge is formed at B at D prime 0, 0. This is the center. And our earlier study says that d prime is a square by d. That is, if the inducing charge is taken much away from the conductor, then this goes, as d goes to infinity, d prime goes to 0. This is one of the important property of the image charge. You consider in geometrical optics the image mirror formula. The mirror formula was 1 by U plus 1 by V is equal to 1 by F. If we write it as this is 2 by A, the radius of the spherical mirror. Here we define the focal length by the condition, definition of focal length. F was that. If U tends to infinity, V is at F. That is, for an object situated far away, the image is formed at the focal plane. Here, note that all the distances are measured from the pole P. All the distances are measured from pole, and any distance measured in the direction of the incident ray, are negative. So AP direction is the negative direction and PA direction is the positive direction. This is the sign convention that we use. So the image charge E, image position U is equal to PA. This is obviously positive. PA, this much is the image distance. The image distance can be written as this much is D and this much is A, so this is D minus A and this is greater than 0. V is the image distance V is equal to PB, and this much is A and this much is D prime, so PB is equal to A minus D prime. This is negative because we are measuring in this direction. And the focal length, we can assume that focal length is F prime, modified focal length. This is negative because we are measuring focal length in this direction. This much is up. So we assume that in electrostatics, we assume the mirror formula to be 1 by U plus 1 by V is equal to 1 by F prime. This is F prime is different from this. F prime will be determined from the condition F prime determined by the condition D tends to infinity, D prime goes to 0. This is the condition. So if we write it in terms of this quantity, this is 1 by D minus A, V is negative, so this is A minus D prime is equal to 1 by F prime with a minus sign. As D goes to infinity, this term goes to 0 and this goes to 0. This immediately leads to F prime is equal to A, not A by 2 as we obtained in geometrical optics. This is the difference. In geometrical optics, the focal length was half of the radius. Here the focal length is equal to the radius. So we modify this definition as in electrostatics. The definition of the image formula is this: 1 by U plus 1 by V is equal to 1 by F prime is equal to 1 by A. Note the difference. Now, this change in the result is due to the different imposition of different boundary condition. In optics, in electrostatics, it is the boundary condition, but in geometrical optics, the boundary condition was different. As U tends to infinity, V is at F. Now, let me apply this condition. We come to this case 1 by D minus A, this is the image distance, minus 1 by A minus D prime is equal to minus 1 by A. We need to know D prime, or we write or changes all the signs. So 1 minus A minus D prime is equal to 1 by A minus 1 by D minus A. When this goes to the other side, this sign will be positive. So this is D minus A plus A. So this is D by A into D minus A. If we interchange the numerator and denominator, A minus D prime is equal to, this will be at top, A D minus A by D. This term is simply A minus A square by D prime. This A cancels, which gives us D prime is equal to A square by D, the location of the image charge. Now come to the magnification. m is equal to minus v by u. This is equal to q prime by q, and if we write the values, we find v is the this is the value of v prime, and this is the value of u, v and u. On simplification, we lands up with minus aq by d. So the formation of image in electrostatics can be looked upon as a reflection in mirrors, provided the mirror formula has been adequately modified with the new boundary condition from which is true for the electrostatic case. The other problem may involve that the conductor is not grounded. If the conductor were not grounded, then the potential on the surface will not be zero. But since the conductor is an equipotential surface, the potential is zero everywhere. Say it is phi 0, which contributes to the coefficient of p0, not to p1, p2, the Legendre polynomials. And furthermore, if the total charge is not zero, or say the charge, some charge capital Q is given to the sphere, the induced charge is Q prime. If Q is the charge given to the conductor, so this will be Q prime plus something has to be added to make this Q the total charge given to the conductor. So in that case, the image charge is not a single charge, two charges has to be placed, and Q prime is another charge to be placed. By symmetry, it should be somewhere on the z axis. The calculation become very simple if we place Q double prime at the origin. So in that case, the potential will be at a point will be due to the three things. One is Q at A, Q prime at B, and Q double prime at the origin, and the rest things are the same. Only thing, the mathematics will be complicated. In the next class, we will conclude our discussion on method of images by considering the image formation at the boundary of two dielectrics. That will be our subject topic in the next lecture.